Hello, welcome back to Algebra. The title of this lesson is, well, I could title it various ways, but the one that I wrote down is what is the difference between the four conic sections? Probably a better title would be definitions of the conic sections. It's a kind of a weird title, but what I want to do in this lesson is we want to go again through each of the four conic sections: circle, ellipse, parabola, and hyperbola, but we want to go a level deeper than we did in the last lesson. In the last lesson, just to recap, we talked about the shape of these conic sections, but we mostly focused on what they're used for. We talked about orbits. Every orbit in space, whether it's a circular orbit, an elliptical orbit, a space probe on an escape trajectory, they all represent each of the four conic sections, depending on how much speed you have in your orbit. We also talked about the idea that a parabola has a special shape where it can take incoming radio waves or light rays and focus them onto a focus. So we kind of talked about the idea that a parabola has a focus, which is kind of near the bottom of the parabola, that collects all of the light rays, right? So if you haven't watched that, I would like you to go ahead and look at it again and make sure that you've watched it. So here we're going to go one level deeper. We're going to talk about the conic sections. We're going to write down the shapes, but we're going to go more deeply into why they have those shapes. And we're going to generally look at the equations of these different conic sections. And we're doing them all in this one lesson, but in the next lesson and the subsequent lessons, we'll be taking each of the conic sections apart in more detail and solving tons of problems. So you can still consider this to be kind of an overview lesson of everything. So I want to recap something very important. I'm going to put my paper down here that we did talk about in the last section. Each of these conic sections can come from slicing a cone. So the first conic section is the one you already know about, a circle. A circle comes from taking a cone and slicing it parallel to the base like this, right across. When you slice it and look at the cross section, you have that beautiful circular shape, equidistant from the central point of the circle. So we all know about circles already. I'm going to put that aside. But what fewer people know is that you can get the other conic sections from slicing a cone. If you take a cone and you slice it at some random angle, this angle is not special, it's some angle I just happen to use my knife to slice it at, and you cut it apart and look at it, the shape you get as the cross section is an ellipse. So this might help if I turn it on the side. It's an elliptical shape, right? Now, of course, the exact shape and size of the ellipse will depend on how you cut it, but you get a circle by cutting a cone directly across. You get an ellipse by slicing it at some random angle, right? And of course, whatever angle that you have there is going to determine the actual shape of the ellipse. And then we take the same cone and we decide to slice it slightly differently. In this case, you notice how this side of the cone has an angle to it, right? So what we do is we slice through parallel to the side. This line here is as good as I can get parallel to this side. So when you slice through parallel to the side of the cone there, then what you get, might help if I turn it upside down, is a parabola. This is a parabolic shape. It comes down, has a nice rounded bottom, but kind of gets to a point and then it comes back up. This is the shape of a standard parabola. Of course, exactly where you cut it and how you cut it, the shape of your cone and all that is going to dictate exactly what it looks like, but that's how you get the conic section known as a parabola. The final conic section we talked about is called a hyperbola. This one is if you take your cone and instead of slicing at an angle or parallel to the other side, you look at the cone like this and you slice it straight down. So you slice straight down, and when you do that, you actually get something that looks very similar to a parabola. In fact, I'll go ahead and show you that they are different. So this one here is a parabola, this one's a hyperbola. Notice this one has a much sharper point to it at the bottom, and it also has much more steep sides to it. That's a hyperbola. And then finally, whenever you cut the hyperbola, you need to really envision it being really two cones. You have one cone on the bottom and then one cone kind of flipped upside down. And when you slice through both of them, you slice through the top cone and go straight down and slice through the bottom cone, you're actually going to get two halves of the hyperbola. So for a circle, you make one slice, you get one shape we call a circle. For the ellipse, you make one slice, you get one shape we call an ellipse. For a parabola, you make one slice, you get one shape we call a parabola. For a hyperbola, when you think of the two cones, you really make one slice, but you're slicing through two different cones. You get two shapes, which they kind of come in pairs, called a hyperbola or a hyperbolic shape. So what I want to do now is I want to pick up the toys here, and we're going to go through each of these conic sections on the board, drawing their shape, showing you exactly how the shape comes about, writing down some of the basic equations of the different shapes, so you'll understand how the different conic sections relate to each other in algebra, and of course, by extension, into geometry. All right, now we're ready to roll up our sleeves and get serious about this. So On the first board, we're going to talk about the conic section that everyone here already understands at least something about. It's called a circle. We haven't talked about circles much in algebra yet. We're going to talk about them at great length here. You all have some idea what a circle is, right? So let me go ahead and try to do that here, to draw that for you here. So here's my best freehand at a circle. Is it a perfect circle? No, it's definitely a lumpy circle. So sorry about that. But this is the best circle I can draw freehand. Now the thing about a circle is, what defines a circle? Well, the center is the thing that defines the circle. So I'm going to put, this is the center of the circle. And you all know that every circle has what we call a radius. So to draw that radius, I'm going to kind of draw a little arrow here. And I'm going to put a point P on the edge of the circle here. And I'm going to call this point P x comma y. Why am I doing that? Because if you can, I'm not going to draw a grid here, but if you can imagine an xy plane kind of where the circle is sitting on top of the xy plane, then what we want to do is we want to write an equation down that talks about the shape of the circle. We want to, yeah, we all know a circle has a center and a radius. Of course we know that, but I want to be able to put it in a coordinate plane and say, what is the equation of that circle? How can I plot that circle? Is a circle a function? Is a circle not a function? We need to talk about those things. So we need to write an equation down that describes every one of these purple points here. So it shouldn't describe points here and here and here and here because those aren't on the circle. The only points on the circle are on the purple line. The points related to the circle are not outside the circle and they're not inside the circle. The only points that describe the circle lie on this purple line exactly. So these points we call P, and we say these points P have xy values. That's what the xy means. So here's a different xy value, here's a different xy value on this part of the circle, and so on. As you go around, you'll have a different xy value for the points on that curve. Now we're going to do a similar thing when we talk about a parabola and an ellipse and a hyperbola. So it's important for you to understand Pxy just means the set of points that describe the shape that we call a circle, and they all have xy coordinates, right? So the way that we write down the definition of a circle is in words. If you were to see it in a textbook, you would see something like this. A circle is the set of all points. I'm going to put P, meaning all of these points P. There's an infinite number of points on this purple line. Set of points P. The same distance from the center. Okay, and so a way that you can write this in terms of a definition, I mean, this is in words a definition, right? I mean, this makes sense. I mean, this is what you all know a circle is. It's the set of all the points, the same distance. That means the same radius from the center of the circle. You all know that the points P are all the same distance away from the center. That makes sense, right? But in mathematical talk, or mathematical parlance, you would say if this is the center C and this is the point P, you would say that CP, the distance CP, must be equal to a constant. Now this does not mean C times P. This does not mean the center times P. This means the distance. You remember in geometry when we talk about distances, we have the endpoints and we write them as, you can think of it as a line segment with a bar on top. The distance between A and B is AB. The distance between XY is XY. The distance between the center and the point P is called CP. And this distance must be a constant no matter what angle I'm looking at. If I'm looking over here, the distance between the center and this point must be the same as the distance between here and here, which must be the same as the distance between here and here. So we're saying that the distance between C and all of the points P must be a constant number. What do you think this constant is? Well, that's the radius of the circle. That's what describes the size of the circle. So that's what a definition of a circle would be. Now, in terms of an equation, right? We're not going to talk too much about the equation of a circle now. We're going to have an entire set of lessons on it. But just to give you a flavor, the equation of a circle would look something like this. A general equation of a circle would look something like this. X squared plus y squared is equal to r squared. And what does this mean? Now, this is a different kind of an equation than we've seen before. I don't expect you to understand this yet. I don't expect you to say, oh yeah, that makes sense. I expect you to believe me. This is the equation of a circle. But once we get through the overview of conic sections, we're going to go back to circles first, and we're going to really dissect why this is the actual equation of the circle. For now, I just want to get all the equations on the board so that you can see how they kind of are similar to one another. All of these conic sections come from cones, from slicing cones. So all of the equations have a similar flavor to them. In particular, you're going to start seeing squares all over the place. In general, when you see something squared in math, it means something is curving in general. And a circle is the shape of a perfect thing that curves. So it has squares everywhere. This r here is what we call the radius, right? So this thing is the radius. So if you make r bigger, then the circle is going to get bigger. So you can say from this equation that r determines the size of the circle. All right, so what I want to do is I want to put the circle on the back burner now, because I think we all understand a circle is the same distance, points are the same distance away from the center, which means the center to point P, no matter where the point P is, must be a constant. This is the equation, the basic equation of a circle. Of course, we can shift the circle around and change it a little bit, but the base equation is what we have written here. But we're not going to get into too much of this yet. We're going to do this later, where the radius determines the size. Now, what I want to do is get the next conic section on the board, and that is, well, you can put them in any order you want, but I want to talk about an ellipse next. Because an ellipse, when you think about it, really looks kind of like a circle, but it's stretched out a little bit. So the equation of an ellipse and the equation of a circle are kind of similar to one another. So let's go over onto this board and talk about the concept. Let me put underline here. This is a circle, and we want to go over here and we want to talk about an ellipse. Right? Ellipse is a very important shape in math. We learned that all of the orbits of all of the planets end up following ellipses. All right? So here's how we have to do this. You have to kind of use your imagination. I need to get some things on the board before you totally understand it. So let me just kind of draw a few things. So let me try to draw my best guess at an ellipse. Is this going to be a perfect ellipse? No, it's not even going to be close to a perfect ellipse. I can tell you right now it's already too flat at the bottom. You know, I should round the corners a little bit, but I'm not an artist. I never claimed to be an artist, so you're just going to have to put up with that. So the shape of this thing is going to look more like something like this. Anyway, that's pretty close to an ellipse. Now, the thing about it is when you look at a circle, there's one special point in the middle. We call it the center, right? But when we have an ellipse, and also the other conic sections, we have not just one special point in the center, we have two special points. And we don't call them the center because they're not in the center. We call them the focus. And when you have two focuses, you call them foci, right? So you have to get used to the idea that there's actually going to be kind of two special points in the center of the shape instead of one for the case of the circle. So one of these focuses, or one of these foci, is located around here, and the other one is located around here. Now, I don't want to bog myself down too much with how I know exactly where the focus is. What's going to happen is we're going to write all this stuff down, and we're going to go in detail and talk about ellipses, and we're going to derive the equations and talk about where they come from. But for now, just know that if you kind of take this ellipse and squish it together so it becomes a circle, then both of these focuses, or foci, kind of end up becoming on top of each other, and then in that case you get a circle. So basically an ellipse is really just a stretched version of a circle. So when you take a circle and you stretch it out, that one center point that's so special, the center of the circle, becomes two special points, and that's called focus number one and focus number two, right? So we're going to actually call this focus number one, and we're going to call this focus number two. And I'm going to label it because it's probably one of the most important things I want you to really learn here. This thing is called a focus. And this thing here is also called a focus. And this is focus number two, and this is focus number one. Right? Now, why do we have these special points called a focus? Well, we need to kind of get into that, right? So what we have here is just like we had in the case of a circle. The shape was described by the purple curve. We said it had points, P, and they had locations X and Y, right? And we wrote down some stuff to talk about where they are. Now, on this ellipse, we have points as well, and we're going to call it the set of points P, X, Y again. So basically, the purple curve represents all of the points. There's an infinite number of points on this curve, right? They're infinitely close together, right? They all form the special thing we call an ellipse. These points have locations X, Y. If you put this thing on top of a coordinate plane, and you could put a location for every one of those points. So how do we determine the special case of the special curve that we call an ellipse? Well, in the case of a circle, it was simple, because a circle just meant that every point had to be an equal distance. So if you lock down the middle and you trace your finger out, then you're going to trace out all of the special points. An ellipse is a little more complicated. So let me draw a couple of things. And I'm going to draw a line segment from here to here. And I'm going to draw a line segment from here to here. All right? So I want you to kind of keep in mind, whoops, sorry about that. Probably should have used a different color. So this is just saying focus number 2. So here's a line segment from here to here and a line segment from here to here. So what you have is, let's see, how do I want to do this? The set of points P that defines this purple curve in ellipse is the following thing. The distance between F1 and P, which means this line here, between F1 and P, plus the distance here, which means from F2 up to P. So this one plus this distance is equal to a constant. Think about what that means for a second. The secret to what an ellipse is all written down in this simple little relation right here. What it means is I take any 2 points in space, call it focus 1, focus 2. And I want to find the set of points that going to go around there so that the distance between one of these points to my shape I'm calling an ellipse, plus the distance down to the other guy is equal to a constant. So what this means is, you can see how I've drawn it here, that works for that one particular point, but let's draw another point. Let's say we pick a point down here. And this point is on the ellipse as well. So this is, of course, P, X, comma, Y as well. It's another point, of course, but it has X, Y coordinates. What we're basically saying, let me draw a little dotted line between this point, and then this point up to this point right here. So you can imagine for any point on the ellipse, you can draw these lines from the ellipse to the border, and then from the border to the other focus. I'm sorry, from the focus to the border, and then from the border to the other focus. So what you're basically saying is, if you have 2 points, call it focus 1 and focus 2, the ellipse is the set of points P, so that as I walk around the ellipse, the distance from one focus up to the border and back down to the other focus is the same number. It's a constant. Just like the distance here was a constant no matter what. It was really simple because there was only one center point. Now I spread the points out and I'm saying, okay, if I move, let's say over here, instead of looking at this point, I look at this point here, then the distance between here and here, that's a little longer, but then the distance between here and here will be a little shorter. So you add them up, you get a constant number. So let's go over here. Let's say you take a point from here, way over here, over here. This is even longer distance than what I've drawn in blue, but then this is a shorter distance, so of course you add them up, you get the same thing. If I pick a point here compared to the blue line, then this distance from F1 to my finger is shorter, but then the distance from here to here is longer. So when I add them up, I still get a constant number. So you see, no matter where I walk on the edge of this curve, if I even pick this one, this is really, really short compared to the blue line, but this distance is much, much longer. So I add them up and I still get a constant number. So just like there's this thing we call a radius, when it comes down to circles, ellipses have a similar constant thing. It's just that there's 2 centers, for lack of a better word. We don't call them centers because they're not in the center. We call them focus 1 and focus 2. Distance between focus 1 up to the border and down to the other focus has to be the same for every single point on that egg-shaped thing that we call an ellipse. So that is what this equation means. The distance focus 1 to the point, focus 2 to the point has to be equal to a constant. And that's why I'm drawing it next to the circle, because it has a similar meaning. Now, if you wanted to write in words what it means, what you would see in a book, an ellipse is the set of points P. Set of points P. It's always going to be the set of points P. Okay, where the sum, I'm using shorthand here, this means the set of points P where the sum of the distance from P to 2 fixed points, and these are called the foci, are the same. Now, when you read this kind of thing in a book, the set of points P, so the sum of the distance between P to 2 fixed points, foci, are the same. I mean, even I know what it means. I read it and I'm like, what does that mean? Because it's just too wordy. All it's trying to say is you pick any 2 points. I mean, literally, I can define an ellipse with any points I want. I can say, here's a point, here's a point. Okay, great, 2 points. How do I find an ellipse? there's got to be some egg-shaped thing we call an ellipse, points that surround those two. So the distance from here to here is a number, and the distance over here is the same number when I add the individual little radii up. So you can think of this as radius 1 and radius 2. You add them up, you get a constant number. You can think for this point, radius 1, radius 2, you add them up, you have to get a constant number, and so on for every point around. Even if you pick a point here, the distance from here to here is short compared to this, but the distance is much longer compared to this one. You add them together and you get the same constant thing. Now, when we get to actually talking about the math here, we're going to derive this. We're going to talk about this in a lot more detail. But for now, I think what I want to do is write the equation of a basic ellipse on the board. And that is the following. I don't expect you to know this yet or understand this yet, but this is what it is. X squared over a squared plus y squared over b squared is equal to 1. This is a basic equation of an ellipse, and A and B determine the shape. What I mean by that is an ellipse can be really long and slender, or it can be kind of fat and stubby. It could also be rotated to go up and down instead of side to side, and so A and B are going to determine how the thing looks. How stretched out is it? That's what we call the eccentricity. Is it oriented vertical or horizontal? A and B are going to determine that. But when you look at it, it looks similar to a circle. There's an x squared plus a y squared. Here's an x squared plus a y squared. So that part's actually the same between the two. Now, in the case of a circle, we just set it equal to r squared. In this case, we set it equal to 1. I'll explain a lot more why it's written this way later. But anyway, the idea is you have x squared plus y squared is equal to something. And now for the ellipse, we have these a and b terms, which really determine the shape, how stretched out the thing is. All right, so that's what an ellipse is. Now what I want to do is talk about parabolas. Now we've been talking about parabolas in algebra for a very long time. You all know that the function f of x is equal to x squared defines that basic parabolic shape. We've sketched them, we've graphed them, we've done tons of things with parabolas because it's one of the most important shapes and one of the most important functions in algebra. But now we're diving deeper. Don't skip over this stuff. We're diving deeper into how that special shape of a parabola comes about. Remember, we actually talked about in the last lesson that the parabola has that special characteristic that it focuses all the incoming parallel rays onto that special spot we call the focus. And we now know ellipses have 2 foci. Parabolas only have 1 focus, so we have to figure out where the focus is going to be and how the shape of the parabola actually relates to that. And so for the third conic section, we're going to talk about parabola. And I know you're parabola. I know that you're maybe rolling your eyes because we've talked about parabolas so much, but I'm sorry, it's just something that it requires a lot of work because parabolas are very, very important. All right, so first let's figure out what is the shape of a parabola. Now, this is a freehand parabola. I'm sorry, it's not going to be perfect. It's probably too broad at the bottom or whatever, but you see it's the general shape of a parabola that you know and love. And but now we want to talk about it in terms of its definition, in terms of the equation, and how this shape is actually really defined in general. All right, so the thing to note about a parabola is that it has a focus also, and we talked about that. The focus is going to be somewhere around here. The exact spot where the focus is will come into focus later on when we talk more about the equations. I'm going to write an equation for a parabola down, but we're going to discuss parabolas at much more great length a little bit more down the road. So we have this special spot that we called the focus, that we call the focus of the parabola. So that means all incoming light rays bounce off and they get concentrated at that point. But here's the part that we have not talked about parabolas in the past. There's also a special line associated with the parabola. It's down here. It's actually below the parabola. It helps define what the parabola is. See, in the case of a circle, all we needed was 1 point to define all the set of, well, we needed the center and the radius to define the set of points we call a circle. For the ellipse, we just needed 2 foci, and then whatever this constant is going to determine the shape of the actual ellipse. Now for a parabola, you need 2 things to define what the parabola is, but it's not 2 foci, or 2 focuses, it's 1 focus and 1 line. This thing is called a focus, so I'm going to write down focus here, right? So call it focus F, but this line has a special word, it's called directrix. directrix. So anytime you see the word directrix, you know it's some line, it's the line associated with a parabola. So this is something we haven't kind of talked about at all yet, so I need to make sure you understand. In the past, we've graphed parabolas, we've shifted parabolas around, we've dissected parabolas everywhere. You probably thought there was nothing left to learn about parabolas. But it turns out to define this special purple shape called a parabola, you actually need two things. You need the focus, which is the spot where the rays are concentrated on if they bounce in. And you also need this special line called the directrix. So we're going to talk a whole lot more about how we know where the directrix is later, but there exists a line underneath every parabola you've ever graphed called the directrix. I never told you about it because we didn't need to know it until now. All right? So we also have another special point, and this one you already know. This is called the vertex. Let's see here. Nope, I don't want to put it over there. I wish I would have done that on the other side because I have some other stuff I need to draw here. So it's over here. We're going to call this the vertex. The vertex is the lowest point of the parabola, or if it's upside down, it's the highest point of the parabola. So given that there is a focus of a parabola, a dot, and a line, in fact, given any dot in any line, you can always define a parabola that goes down in between these two things. How do we define what it is? Well, similar to what we've done before, we have to draw a few things. All right, what we say is that from the focus, the distance from the focus to the parabola, here's a dot here, and the distance from this point down here to the directrix is the same distance. They're equal to each other. So I'm going to put a line through it. This is from geometry. This line means this thing is congruent, which means it's equal to in length this one. Now the way I've drawn it, this line's actually slightly bigger. That's just because I'm drawing it freehand. But what I'm trying to tell you is that for every parabola, you can make this little argument that the distance between the focus to the point P and the point P to the directrix is the same distance. So this little cross mark means this is the same distance as this one. And this relationship that these are equal is true for every point on the parabola. In fact, if you look over here, if I draw, for instance, maybe over here, this distance is the same as this distance right here. And of course, that's not exactly right because I drew this thing freehand. The actual shape of the parabola is not quite the way I've drawn it. And also, maybe if you go up here, the distance here, and then also the distance down here, this should be the same as well. And the more I look at this, the more it's not quite right. And the reason it's not right is because my parabola is too narrow. It should be drawn a little bit wider like this. So you know what? Let's try to fix it. Why not? We've got time, and it's really important. So I want to try to fix it for you. It's not going to be exact, no matter how hard I try. But let me go here and let me kind of take these out a little bit here. If I go and do something like this and say, okay, something like this, maybe that's a slightly better shape of a parabola. Maybe something like that. Okay? So then, if you look, let me take these away. Okay? What I'm trying to say is that the distance between the focus and this spot right here is the same as the distance down here. So these are equal. This looks a little better. The distance between here and here and here and here is equal. It's a little better. It's not perfect. The distance from here to here and then here all the way down here, these are equal. So it's pretty close. It's not exactly right, but it's pretty close. You can see that the set of points that are the purple points, and actually I'm going to call them the same thing I've been calling them, P, X, comma, Y. So this is P. All of these points are called point P everywhere here. This is point P, this is point P, different point, different coordinate X, Y, but we all call them the set of points P. The distance between the focus and the point on the parabola is the same as the distance from the parabola down to the directrix. Now, we've never had to draw the directrix before because I was just giving you the equations of the parabola before and just telling you to draw it, plot the points and draw it. And I told you that f of x equals to x squared is a parabola. I told you that. But I never told you why it was a parabola. I never told you what's special about a parabola. What is special about a parabola is the distance from the focus to any point on the parabola is the same as the distance from the point on that parabola down to this invisible line called a directrix. Right? So if you wanted to write a definition, a mathematical definition of what this is, then the way you would say it is the distance FP, the distance from the focus to the point P, is the same as from point P to point D, where we call this distance the directrix here. So you could say, you know, this is D1, point D2, point D3. like this. So the set of points on the directrix is called the points D, the set of points on the parabola called the set of points P, and the focus is just one point. So the focus to the point on the parabola is the same as the distance, that same distance from the parabola down to the directrix, from point P. Whatever point you pick on the purple curve is going to be true. Even if I go this way, the distance between here and here is the same as between here and here. If I go down below, the distance between here and here is the same as between here and here. If I go way over here, the distance between here and here is the same as the distance between here and here. And that is what a parabola is. It's a special shape that kind of cuts through between the directrix and the focus in such a way that those distances are the same. So what you would see in a book would be something like this. A parabola is the set of all points equidistant from a fixed line and a point, which is called the focus, not on the line. Right? So basically, if I pick any point, call it the focus, and I pick any line, call it the directrix, I can always find a set of points that will cut down below the focus and above the directrix and cut through like this. So the distance between here and the curve is the same as I've outlined it here. Now, what is the equation of a parabola? Of course, you all know what it is because we've used it so many times, but the basic equation of a parabola is y is equal to a times x squared. So notice that this one's different than the other ones because I have a square on the x term, but I do not have a square on the y term, right? Notice here I have a square on the x term and a square on the y term. Yeah, there's some other junk here, but this is a closed shape because I have squares on both of them like this. And then I have squares on both of them here as well for the circle, so that's a closed shape. Parabola is not quite the same. I don't have a square on the y term, I only have a square in the x term. And of course, this variable a was very important. The a determined the shape. So this variable a determined the shape of the parabola. Specifically, if a is really large, like if it's 100x squared, you have a really narrow parabola, really tight, right? If you have a very small value for a, like 0.01 x squared, then your parabola is enormously huge. It's like really broad, really shallow. So in each of these equations of the conic sections, you have certain little numbers that determine the shape of the thing. And of course, we know that we can go in here and shift in this parabola in the x direction by putting the term inside of this x variable. We can shift in the y direction. So we can, of course, shift the parabolas, the circles, and the parabolas, the ellipses, and the circles around by playing around with what's inside of the variables here. But these equations I'm writing down here are just representative basic equations. Now, the circle, the ellipse, and the parabola are, I don't want to say they're easy, but they're easier to understand. The hyperbola actually is a little weird to wrap your brains around, but it's not so hard to understand it when you understand where you're coming from here. You know, you have the set of points in equal distance from a center. Okay, and then this is the set of points where you're adding together these two kind of line segments, and whatever the sum of them are, you're getting a constant number. This defines the special shape. We can pick any point we want on this purple curve, and I can take from here to that point, and from that point to here, and I can add it up and I'll get a constant number. That's what the ellipse is. Keep that in mind as we go and talk about what a hyperbola is. So we need to write a hyperbola down. I know we haven't talked about hyperbolas yet much, but this is the introduction to what a hyperbola is. It's very important, actually. All right, so now what we need to do is draw the shape that we call a hyperbola, and we have two kind of mirror images here. These are not going to be great drawings. I'm sorry about that. It's hard to do this freehand, but I'll try to do my best. But they basically form these shapes. If you turn your head sideways, remember how we cut that cone? It would produce one shape angled down and one kind of shape angled up, and they kind of face each other because the cones were pointed toward each other. But anyway, that doesn't matter so much. We have this shape called a hyperbola. This purple shape is what we call a hyperbola. Both halves refer to the single thing called a hyperbola. This thing is not a hyperbola, and this is a separate hyperbola. They both form this thing called a hyperbola together. Now, just like in the case of an ellipse, we had a focus, right? and also for a parabola as well. So here we have a focus for this hyperbola. We have a focus here as well. So we call this one focus F1, and we call this one focus F2, you might imagine, because we have two focuses. Now, this is why it becomes a little bit weird to think about. I need you to think about the ellipse, though. We had the two focuses, and what we did is we said the distance from one focus to the point on the ellipse plus that distance from the same point down here was a constant. We had to add those two kind of radii together. If you want to think of a kind of sort of like a radius, we add them together and we get a constant. For hyperbolas, we need to do subtraction. That's why it's a little hard to visualize. So let's say there's some point here on this hyperbola, and let's say it's where do I want to draw this? Let's call it P1, x, comma, y. Okay. So what I'm saying here is that the distance between here and here, and then we have a distance here and here. So in order to, well, it's probably going to be easier to show with another point as well. We have, let's call it P sub 2, x, comma, y, right? So let me draw another one as well, make it a little easier to understand. So then we have the distance between F1 up to here, and then the distance between here down to the focus as well. So what we're basically saying here is that the distance F1 up to the point P1 minus the point P1 down to F sub 2, this is the exact same distance as whenever you say point F1 up to P2 minus P2 to F2. And another way to really say this is the distance in general from point F1 up to point any P on the parabola minus that same distance, point P, but to the other focus, is going to be equal to a constant. So when you really think of it this way, it's very similar to the equation of an ellipse. We added together the distance between the focus and the point on the parabola. We had to add them up and we got a constant. Here we're subtracting them. Now, what I need you to understand is more than just the math here. I want you to intuitively understand what it means. If I look at this point in blue here, the distance here, and then if I subtract this distance here, that's going to give me some number. Let's pretend this is like 6 centimeters and this is like 2 centimeters, so I'm going to subtract them. I'll get 4 centimeters. But if I take the distance between this and this other line, that's going to be a longer distance than this line. It's longer. But then I'm subtracting off a longer distance as well. So when I do both sets of subtractions, I'm going to actually get the same distance. Because no matter where I walk on this parabola, if I walk all the way down here, but then I'm going to take this, but then I have to subtract off this distance, which is also longer, then I'm going to get the same thing. That's why we say it's a constant. So in general, the hyperbola is similar to the ellipse in the sense that you're kind of taking two distances and you have to get a constant out of them. But in the case of the ellipse, we add those distances together and we say that we get a constant. In the case of a hyperbola, we subtract those distances and we say that we get a constant. So this is what basically you get here. Now, in terms of what you might see in a book as far as like the definitions of a hyperbola, it's the set of points P, so that the difference between such that the difference between the distance from, this is why it gets hard to understand it, from P to two fixed foci, these are points, right, is a constant. Now, if I give this to anybody and just say, hey, here's what a hyperbola is, you're not going to understand it because it doesn't make intuitive sense. The set of points P, so the difference between the distance between P to two fixed foci is a constant. It's so hard to understand. All it's basically saying is, pick 2 points. We call it focus 1, focus 2. There must exist 2 purple curves in there so that the difference in the distance between this to one of the points on the curve and the point on the curve to the other focus is the same. And that very special shape so that you always get the same number when you do the subtraction, meaning it's a constant, is called an ellipse. I'm sorry, is called a hyperbola. I'm sorry about that. Now, the equation for a hyperbola looks like this, the basic equation, x squared over a squared minus y squared over b squared is equal to 1. Now, of course, we can change it. We can shift the hyperbola around by doing shifting and all this, but notice this has a very similar form to the ellipse, and that's because the constraint is real similar. See, we had a plus sign here when we're adding up these little segments to get a constant, so we have a plus sign here. Here we're subtracting the two segments, so we have a minus sign. So they're very similar to one another, right? But the idea is that you have a subtraction going on. The a and the b term are going to also determine, a and b are going to determine the actual shape of the hyperbola. Is it going to be really broad, or is it going to be really, really narrow coming in and out? And also a and b will determine if it's tilted up and down along the y-axis or if it's extended along the x-axis as well. Now, the purpose of this section was not to make you an expert in conic sections. That actually takes more time. But what I wanted to do is give an overview of what the different conic sections are in more detail than we did in the last lesson, to talk about mostly the definitions of what the set of points for circle, parabola, ellipse, hyperbola are, and to also write the equations down, not so that you understand them yet, because I don't think you really should understand them yet, but just so you can kind of see the similarities. So for a circle, it's a set of all points an equal constant distance from the center. It has the equation of this form. You have a square in the x term, a square in the y term, and you have a single number we call the radius, which determines the size of the circle. For an ellipse, it's similar. You have kind of the distance from the central point to the point on the edge. We call it maybe radius 1 if you want to, and then you have to add to it the other kind of quote-unquote radius from the other special point to the edge. We add them together and we get a constant thing, but it in turn produces an equation like this. You still have the x squared plus the y squared. You have a number on the right, but then you have two numbers. The two numbers dictate the shape of the thing. Is it going to be really long and stretched? Is it going to be fat and stubby? Is it going to extend in the x direction? Is it going to extend in the y direction? This will determine, and also other things that we'll talk about later, the shape of this ellipse. Then we had the famous parabola. We never learned before that we had a directrix that exists below every one of these parabolas. You pick a special line called a directrix, you picked a focus, and you can always draw a curve that goes between the two such that the distance from the focus to the curve and the curve to the directrix is the same, right? So the set of all points equidistant, blah, blah, blah. And so when you do the math, which we will do in a few lessons, you'll find out the basic equation of a parabola looks like this. A single number determines the size or the shape of the parabola, how squished it is, how broad it is. Notice we only have one square in the x term, we don't have a square on the y term, and so the parabola is opened up like this. Next, we finally have the hyperbola. Actually, it shares a lot of characteristics with the ellipse. You can kind of think of a hyperbola as an ellipse that's been stretched so much that it kind of flips back on itself and kind of becomes opened up into this hyperbolic shape like this, and it is defined to be the distance from one focus to the point on the curve minus the distance between that point to the other focus is a constant. And the equation you get looks almost exactly the same as an ellipse, but you have a minus sign instead of a plus sign. There are a lot more details to this. We're going to get into all of them. Now what we need to do is we need to talk about circles in great detail, how to graph them, how to shift them, what the size and shape looks like. We'll do the same thing for parabolas, we'll do the same thing for ellipses, we'll do the same thing for hyperbolas, and by the time you get to the end of it, you'll understand all the conic sections, where they come from, how to graph them, why they're useful, and how to, in general, solve almost any problem that someone can throw at you with regard to conic sections.